Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in this particular video here, we're going to continue from where we stopped. We talked about some interesting things involving the diffusion coefficient, where one, based on our previous video, we looked at how diffusion coefficient relates really well with the specific cross-sectional area of our molecule, where an increase in the diffusion coefficient favors a smaller molecule more than a larger particle. And on the other side, we looked at diffusion coefficient increasing with increasing temperature, therefore hotter molecules will diffuse faster than that of cooler molecules. And the final one here is relationship between the pressure and the diffusion coefficient. And based on this, we are going to arrive at tackle this particular question, which say we should calculate the diffusion coefficient of, or the diffusion constant of, nitrogen gas at 25 degrees Celsius and at this particular pressure, which is 10 pascals. So in this particular case, there's some other things that are kind of missing here, but you will need a specific table to gather those information. Like for example, we're going to need the following. First, of course, we know our pressure to be 10.0 Pascal, which is the standard unit that's going to be used. And we have our temperature of nitrogen gas, which is 25 degrees Celsius. We know that we need it in kelvins, which is in this case plus 273, which will give us this value 298 kelvins. And the next variable that we need to take into consideration are, first, we need a cross-section area of nitrogen gas. And the cross-section area of nitrogen gas is around 0.43 nanometer squared. And to convert this, we need to multiply this by 10 to the power of negative 18 meters squared in order for we to get our value converted from nanometer squared to meter squared. Therefore, this is equal to, for nitrogen gas. And so once we have all these variables, we have other things here like the constants. We know our value for the gas constant, or ideal gas constant in this case is 8.314. Take note that it is measured in joules per mole per kelvins, and we know that the other constant, which is our K value, is around 1.38 times 10 to the negative 23rd. Take note that it is measured in joules per Kelvin. So therefore, based on this, we are going to look for what is required, and our required here is actually based on the question, which says we should determine the diffusion coefficient. And we know that the diffusion coefficient is represented as D. And so where D is the diffusion coefficient or constant, this will be important based on our derivation and our analysis from our previous video, where our diffusion coefficient is measured in terms of D is equal to 1/3 lambda C bar. So in this case here, in terms of our analysis, we know that based on our diffusion formula, we will need to rearrange some terms and variables to fit into the given. So where our D is equal to 1/3 of the mean free path multiplied by the mean speed, we know that our mean free path is equal to, first, in this case, K multiplied by our temperature over our pressure times our cross-sectional area, which is what we have, and also multiplied by square root of 2. And the other one here is our C, which is our mean speed, to be equal to the square root of R8 multiplied by our RT all over our pi multiplied by m, which is the molar mass. Take note that we're using the R and the big M, not the K and the small m, because we don't have the mass of that one atom. So we're going to use our molar mass in here. So therefore, in this particular case, we are going to put these two equations here in this equation, and we are going to reevaluate what our D is going to be in terms of the givens in the question. So take note that since we have this, we are going to put our givens in this particular equation, and we're going to solve for our D. And so our D, which is now in terms of the variables in the givens, is now 1/3 multiplied by, take note that the unit of our K is in joules, and we know that joules is measured in newtons, multiplied by meter, and this is all divided by kelvins, and we know that our kelvin's temperature is around, in this case, it's kelvins, and this is all divided by our specific pressure, pascals. We know Pascal is Newton meter squared, and we are going to be multiplying our Pascal, which is our pressure, by the cross section of our molecule, and this is measured in meters squared, and finally here is multiplied by square root of 2. So this is one part, and the other part is now the other inside bracket, which I'm going to bring that down, and the other bracket here has the square root, and in here we have 8 multiplied by R, which is joules. Of course, is measured in Newton meter, and this is per mole. Take note that is multiplied by Kelvin as well, and on the other side we are multiplying this by our temperature, which is kelvins, and this is all divided by our pi multiplied by our molecular weight, which, take note, is what expressed as kilograms per mole. And so therefore we know that we forgot to explore that on our givens, but we're going to do it right here. We know that the molecular weight of nitrogen gas is 14.01 times 2, which is 28.02, and take note this, it is going to be in kilograms, therefore it will be 10 to the power of -3, and we have kilograms per mole. Take note here that newtons is expressed in kilograms per second squared multiplied by meters. So therefore we're going to reevaluate our units, saying that hey, the unit actually matches our derived unit from our previous video. So in here, kelvins cancels out our kelvins, we have our meters squared cancels our meters squared, we have our newtons canceling out our newtons, and we are left with meters in this particular space right here. And then on inside those particular square root, we have a couple of things canceling out, like our kelvins canceling out our kelvins, we have our mole, yes, canceling out our mole, and we have our kilograms canceling out our kilograms, and what we're left with is meters squared divided by our seconds squared. And as a result of that, we are able to now reevaluate our D, which is now in terms focusing on the bracket, including the 1/3, will give us our value to be, and this is measured in this case in meters, because we have our meters right over there. So therefore, and so what we have here is now our meters squared is going to be canceling with our square root, and what we're left with is our meter, and then our seconds squared in this case here will cancel in terms of the squared, and what we're left with is the seconds. And as a result of that, once you do the square root of all the constants in this square root, we're going to have our number to be 473.514. Take note that this now will be in meter per second. Therefore, our specific diffusion coefficient, is finally going to be our value. Once you multiply the constants, we have 0.10696. In terms of the unit, meter times meter gives us our meter squared, and this will be over our seconds, which is actually matching our specific unit that was expressed in this particular previous video right over here. So that is really remarkable to see how everything agrees really well with our solution, and in this solution we're able to rightly derive the diffusion coefficient of nitrogen gas at a specific temperature, which is 25 degrees Celsius, and at that particular pressure. So thanks for following me through this. I truly appreciate it. Hope you found this really informative in not only being able to understand the overview of diffusion coefficient in terms of its relationship with the pressure, temperature, the molecular weight, and also other interesting things involving the mean free path and that of the mean speed, but also being able to see how this is going to be balanced with the units and satisfies the unit based on our derivation process on our previous video. So all the same, hope you found this really informative. Hit a comment down below, let me hear your thoughts. By that way, I can talk to you all soon. Stay smart as always and believe in yourselves.